The weird obsession that some physicists have with the fact that the usual formulation of quantum mechanics uses complex numbers, or that complex numbers are useful in expressing the physics of quantum mechanics, is just reaching its maximum exponent with this recent paper that has appeared in Physical Review Letters, which by all accounts is one of the top tier, most high impact journals in the entire field of physics. Let me just start for a moment with the announcement by the American Physical Society of this paper using a obviously AI generated graphic that is just truly embarrassing for a professional society to use something like this. But one thing that this poorly generated graphic gets right is that the only thing that happens in the paper really is that the authors are identifying complex numbers with pairs of real numbers, the real part and the imaginary part of a complex number. This is, of course, dressed up in the fancy terminology and notation of quantum mechanics to make it look like there is something sophisticated happening, but at the heart of the paper, all that is happening is that they are using, instead of complex numbers, they are using 2x2 matrices with real coefficients. Because matrices of this form have a matrix, the identity matrix, that works as the number 1 in the complex numbers, and the matrix 0, -1, 1, 0 that works as the I in the complex numbers, because that matrix square is minus the identity. So you can rewrite any of those matrices as a real number A times identity plus a real number B times this matrix that represents I. And here's a clip from the paper where they are doing exactly that. Now, to show you that you can actually do quantum mechanics using this representation of the complex numbers just in terms of real matrices, what they are going to show you is that they can do composition of quantum systems using this representation of the complex numbers. A d-dimensional quantum system is nothing else than a d-tuple of complex numbers, and the composition of two quantum systems is nothing else than their tensor product. So in the paper, they're going to show you that they can do composition of two-dimensional quantum systems just over the real numbers. But if you're identifying the complex numbers with R2, then an element of a two-dimensional quantum system would be an element of C2, so it would be an element of R4 in your identification. If you're doing a composition of two-dimensional quantum systems, you would have an element of the tensor product of C2 with C2, or an element of the tensor product of R4 with R4. But however, those two spaces cannot be isomorphic. That cannot be right because the tensor product of C2 with C2 is 8-dimensional over the reals, but the tensor product of R4 with R4 is 16-dimensional. What's the solution? That to have an actual isomorphism of those two spaces, you need to have some sort of quotient of the tensor product of R4 with R4 that does the correct identification of these two tensor products. And that is exactly what they do. They tell you what that identification is, which is honestly a problem in abstract algebra maybe at the level of graduate school, first year grad school in mathematics. That's all that is happening in that identification. And that's it. That's literally it. That's all that happens in the article. Replace the complex numbers by 2x2 matrices of this form and replace the tensor product of complex numbers by a tensor product of elements of R4 modulo an equivalence relation. So it literally boggles my mind that a paper that is built on some basic concepts of isomorphisms of the complex numbers and basic properties of tensor products appeared in a top-tier journal in physics. It just seems that it's all based on an obsession by some physicists to exclude imaginary numbers from a formulation of the physics of reality. And at the same time, they are okay with expressing reality in terms of probability wave functions. It just makes no sense.